Hello everyone, welcome to the session 2 of week 4. Like you have learned about many applications of additive manufacturing and various case studies in the session 1, in this session as well you will learn about various applications, for example in oil and gas, in construction, in consumer goods and automotive. We will learn how additive manufacturing can add value to the product, how it can be beneficial to use additive manufacturing when you are working on a new design and you are just trying to make a prototype, and if needed how quickly you can adapt the changes in the design. Let us begin with automotive related examples. The first example that we have here is of Hilov manifold. This is a component which is used in high torque plowing systems. As you have seen, it is an example of additive manufacturing in automotive domain. The material that has been used for this application is aluminum silicon tin magnesium alloy, which is originally a cast alloy, and since the original part was made using this alloy, in additive manufacturing also a powder of similar composition is used. And this was also pointed out when we were discussing about metals for additive manufacturing, that it is important to use the same composition so that we can have a good control on the final properties of the component. This application shows the competency of additive manufacturing in design for additive manufacturing. For example, if you have decided to make something using additive manufacturing, we need to adapt that design for this new process, that is AM, and it can be right away printed. And once your CAD design is ready, we can build a process around it and we can do process parameter optimization to see if the properties are as we desire or as if they are good enough for the final component, or are they competent with the existing product properties. This product has various channels. It has some broad inlets, it has smaller diameter channels. The overall size of this product, as you can see, is 213 by 167 by 81 mm, and some of the channels in this product are 8 mm, that is the inner channel diameter. By using additive manufacturing, we could customize the build parameters and the desired geometry and topology could be achieved. The inner channels were clean, and if there were any remnants of the powders or additional sintered part, they could be cleared, and the basic tests for the media flow etc. are currently being done at the client premises. Overall, the value that was added using additive manufacturing for this product was there was faster iteration when the design changes were needed. It also offers better functional design, because as you have seen in this, there are finer channels, there are larger diameter channels and so on, and all these parts have different properties. So, all that could be printed using a single process cycle. It also offers better functional performance. The next example that we have is of rear upright bracket. It is a component which is used in electric automotive racing vehicles. The original component was made using casting process and weighs about 479 grams. the component that was printed using additive manufacturing using titanium 6 aluminum 4 vanadium alloy weighs about 248 grams. So there is an approximate weight reduction of about 52%. The size of this component is 213 by 87 by 41 mm, and just by using the additive manufacturing process, there was also some property enhancement. There was 35% increase in stiffness, and also there was some improvement in the strength of various parts of this component. This component, as mentioned earlier, is used in electric automotive racing vehicles, and it connects wheel axle hub with the brake calipers and also with the suspension assembly. Thus, as you can intuitively have realized now, that it carries high remote loads from rest of the assembly. This is an example of how we can design for AM directly, and once the design is ready, how to build the component and how to achieve the required component with desired properties using parameter optimization. The values that additive manufacturing process added to this component are fast iteration. We can change the design and the process iteratively by without any need of change to the any tools that we use or molds, etc. There are less dependencies. We have a much better functional design, and we also have much better functional performance. Here is a mixing unit which is used in automotive exhaust system. This is another example of application of additive manufacturing in automotive domain. The material used for this assembly is aluminum silicon 10 magnesium, which has about 10% silicon, as you may remember from the session for metals for additive manufacturing. It has various channels which are used in the exhaust system, where various fluids, gases are mixed for heat transfer and so on. This particular example is demonstrating how technology can be built for developing a specific component, and how build and process optimization can be done by using additive manufacturing. There are various value additions. We have faster iteration because of ease of design and process optimization. We have flexible production. That means the additive manufacturing of this component can be done either at the client location or wherever, let's say, the breakdown happens, or we can even change the material if we need. We can change the design as if we are trying to improve the performance of the component. This is again also demonstrating that we do not need any specific tools to make this component. So as soon as we have a design ready, we can print it using additive manufacturing. So we can build the process parameters based on whether we are able to achieve the target properties. We can build those parameters around our AM process, and we can achieve what is required. There are also various inner channels in this. So clean channels can be achieved if there are any remnants of powders or extra sintered components. Those can be cleaned using various available post processing operations. This component is also undergoing testing at client premises. Inlet and exhaust rocker covers are another good example of AM application in automotive domain. These parts are also from the exhaust system of automobile. We have about 3.5 mm mating groove, which is this groove here, and there is about 5 mm rib width, which is the width of this particular rib here, right. The overall size of this component is 179 by 119 by 53 mm, and this requirement came from large two-wheeler manufacturers who wanted to try a new design, a new concept. So in such cases, it is not beneficial to first develop tools and molds. Much easier idea is to come up with a CAD file of the required component that we have envisioned and print it using additive manufacturing. Of course, to meet the properties like we have emphasized earlier, we have to choose a material, and traditionally it is a good idea to start with the material that is used for making conventional components of the same type. So in this case, aluminum silicon 10 magnesium was used. This is a demonstration of design for additive manufacturing. It also demonstrates how build and process parameter optimization can be done. The value added because of additive manufacturing is that we can change the design and process quickly because there are no other dependencies, for example tools and molds, etc. We can also have flexible production using additive manufacturing, and as mentioned already, this is a toolless production process. In this case, it is very important to see, like in other examples also, that there are several cavities, there are grooves, and there are thin sections as well, and even with those there is no need of having any prior tooling or molds. Exhaust expansion is another example of additive manufacturing in automotive industry. This particular set of components are used in tractor industry, and their application is in emission system. Traditionally they are made using casting process. The idea here was to optimize overall manufacturing by using additive manufacturing. Inconel 625, which is a nickel based superalloy, was used, and since there were longer lead times when casting process was used, the application of additive manufacturing was sought and it was successful. The prototyping time or cycle definitely is reduced. There is no need of making tools and molds for this. As we have seen in other examples, these components can be directly printed using additive manufacturing, and as soon as it is printed, it is ready to go to application, to market. The size of these components is approximately 70 by 110 by 90 mm. The flange thickness that is there in these components is about 4 mm, and these fixation points are about 4 mm dia. Right. So, we have fairly integrated geometry in this, but the manufacturing was possible using additive manufacturing. This is a demonstration of how technology can be built for a new product by making quick prototypes using additive manufacturing, and various values were added in the final components. For example, since the material, a new material could be tried, we have superior properties. Also, these superior properties can be achieved by optimizing the process. We can try different processes quickly because iterations are quickly possible in additive manufacturing. So, superior properties can be achieved. Also, the number of manufacturing steps can be reduced heavily, and these parts can be quickly produced from prototype to final deliverables. PTO cover is another example. This is used in tractor manifold, right. So, it is a good demonstration of additive manufacturing again in the automotive domain. This component is about 190 by 230 by 120 mm. The shaft dia that we see here is about 36 mm, and the wall thickness is 6.5 mm, and the gallery dia that we have is 14 mm. The initial component, which was made using casting, was 7.1 kg. Also, the design was a bit different. So, for AM the design was changed. Thus, this is another demonstration of how we can design specifically for AM. The design will have certain values added to it. The original component is 7.1 kg, the new component is 2.2 kg, so definitely there is a weight reduction here. This is a demonstration also of how technology can be built around a component, and this is also a demonstration that even if we have complicated geometry involved, very little or no post processing is needed, and the components thus printed are readily available for usage. This example shows how additive manufacturing adds the value to the product. In this case, we have a homogeneous structure. That means even though there are complicated parts in a single component, we don't need to make the parts separately and then join them. All of this can be printed in a single build. We have optimized post processing. So usually a good surface finish can be achieved by optimizing the process, even if there are some issues related to the surface roughness, etc., etc. Those can be minimized by choosing the process optimization and then choosing the right post processing step. We have a good functional performance here, since in this case there are complicated geometries involved. We can also make use of various materials if needed in various parts, and the functional properties can be achieved, and it will also demonstrate good functional performance. We are going to look at some examples of oil and gas domain. Spray nozzle is the first example. This is a geometry which is 63 mm diameter and 140 mm length. Traditionally, it is built using 10 small components, and those are integrated to this single component. There are various nozzles here, and the nozzles are of various diameters, varying from 12 to 3 mm. As you can see, some are bigger nozzles, some are smaller nozzles which are used in spraying operation. The alloy that is used to make this component is Inconel 718, which is nickel based superalloy. This component demonstrates how we can design specifically for additive manufacturing. Also, how the build process can be optimized and the additive manufacturing process can be optimized to achieve the required property. In this case, we have several value additions. We have a homogeneous structure. In case of casting, depending upon what is the geometry around which there is liquid metal flow, the properties may change. However, in this case everything was built using additive manufacturing. The properties and the structure specifically of the build was homogeneous. We have better functional design because wherever the complicated geometries were supposed to be printed, that was possible using AM, and also the material workability issues were not there, since additive manufacturing process has a good control on the complicated designs and geometries involved in the component. Another example in oil and gas is compressor valve. Compressor valves are used for controlling pressure before it goes to compressor. It is also used for taking natural gas or various fluids, for example from well to the compressor. They can also be used for controlling the process parameters. As you can see in this compressor valve particularly, which is shown here, there are various smaller parts. There are these pins. These pins are of 6.3 mm diameter. There is a small step in this top cylinder, which is another part. This step is 1.42 mm. And then the third part in this geometry is this central region. Using additive manufacturing, all of this can be made in a single build. These pins are required to carry substantial force, 165.47 kilogram force. There are 29 parts which can be built as an integrated part using additive manufacturing. The size of this particular geometry is 197 by 176 by 119 mm. If we make it using additive manufacturing, we have homogeneous structure because it can be created using a single alloy. In this particular case, stainless steel 17-4 precipitation hardening alloy. We also can get better functional design because we can make each part up to the precision, and also since it is made up to the precision, we have better functional performance. Moreover, if needed, all these parts, for example pin, the central part, these channels and the upper cylinder or any openings, they can be made using different materials if needed. This application shows how designs can be made specific to additive manufacturing and how they can be iterated for better process optimization and to get a better build or final part. Valve stems are another examples that can be built and are being built using additive manufacturing. Valves are used for separating various parts of piping, or if there is any leak, they can be used for blocking that leak, or if any part of piping needs repair or any checks, these valves can be used. This particular valve is made of Inconel 718 nickel based super alloy. The stem length is 135 mm in this case. The channel length is 114 mm. The inner diameter is 3.2 mm and the outer dia is 19 mm. When this part is made using additive manufacturing, these channels can be made during the build. In conventional processes, for example forging, this channel has to be made after forging using machining. The length to dia ratio of this channel is 35, which is quite high, and it is quite challenging to make this channel using process like drilling. This application shows how design can be made specifically for additive manufacturing, how build technology can be evolved as required by the application, and how post processing can be minimized when such complicated geometries are made using additive manufacturing. This offers homogeneous structure, a single material can be used here, and since it is made in a single build, the properties of the whole structure will be homogeneous. We can optimize post processing. If needed at all, little bit of cleaning of these small channels can be done, and if the process is very well controlled, even that is not required. Since the part is made to precision, it offers better functional performance. Now we move to applications of additive manufacturing in nuclear power industry. We will talk about few examples which are proof of concept and are currently being tested by the end users. The first example is telescopic tubes. Telescopic tubes are used for installing fuel tubes in a nuclear power reactor because the region where fuel tubes are used is not safe because of high temperature and more importantly because of very high radiation. These telescopic tubes are called so because many tubes are used inserted into one another in this fashion so that larger lengths can be achieved, In the finer most diameter, the object of interest is held. In this case, maybe fuel tubes which are inserted. Each tube which are shown here is of 400 mm length, and in this telescopic arrangement longer length can be achieved. This particular tube is made of stainless steel 316L. Machining or extrusion can be used for making each of these tubes. However, because of the long length, which is 400 mm in this case, machining is not possible, and 316 stainless steel cannot be extruded. As a proof of concept, additive manufacturing was applied, and the finally made part, which is tube in this case, is being tested by the customer. The diameter of this tube is 78 mm, the thickness of the tube is 1 mm, and each tube carries 40 to 50 kg load. This application demonstrates how additive manufacturing needs specific design, and that design can be easily created using CAD. And second, how the build parameters can be optimized over quick iterations. This application demonstrates that using fast iterations, better functional performance can be achieved, and the material workability issues, for example, stainless steel 316 not amenable to extrusion, can be avoided in this case. The second example is regenerator. A regenerator is a device which is used for heat exchange. In this particular case, this regenerator needs to have 67% porosity. Either it can be made using a metal foaming process, which is not very easy. Using additive manufacturing, we can create complicated geometries, lattice structures, and various topologies which can be designed in such a way that very high porosity can be achieved. The material used here is stainless steel 316L. The diameter of this part, the inside diameter is 72 mm. Overall geometry, the outside diameter of this device is 108 mm and the height is 48 mm. This application demonstrates how designs can be made for additive manufacturing, and how build and parameter optimization can be achieved. We can create complicated geometries like this very easily in additive manufacturing. It's a very nice demonstration of that. Also, the topology and the shape and size of such regenerators can be achieved very easily. They can be customized as per the specific end user application. This is just one example of a regenerator. Also, since these complicated topologies can be achieved easily to tolerance using additive manufacturing, it also offers better functional performance. Now we will talk about how additive manufacturing is being used in construction domain. As one can imagine, unlike in additive manufacturing for engineering or heavy engineering domain, in construction particularly, the devices that are used are very large. Since the manifolds and the structures in construction domain are very large, either the platform itself needs to be moved or we need to use very large robotic arms. The first example shows building of a large dome shaped structure using mobile printing device, using large robotic arm. As you can see, there are two concentric walls here. The first wall is shown here and the second wall is just outside. There is a small gap also the structure when finally made is supposed to be like this. Such a geometry cannot be achieved without moving the platform itself, because the sizes here are not in mm or in centimeters, they are in meters. The term big area additive manufacturing came from construction domain only. In the second example, 3D concrete printing is shown, which is being done using extrusion process. Each layer can have thickness of few millimeters. The ingredients are premixed and they are extruded through this channel, and the required geometry can be achieved by controlling this deposition arm, as it is done in metal or polymer or other types of additive manufacturing techniques. Another interesting example of how additive manufacturing has been used in construction domain is this particle bed process, which is done using a D-shape printer. It is called a D-shape printer because this assembly here, which injects water on a bed of ingredients, for example cement, concrete or other ingredients, is of D shape. There are two rails here. The lower rail spreads the particles and also levels it. The top rail runs over this bottom rail and is used for controlling how water can be sprinkled. The lighter part here is a powder bed which has all the ingredients like mentioned earlier. The darker part is the one where water has been sprinkled already. It is similar to how laser is moved on top of a polymer or metal bed. The water is sprinkled only where we want the final geometry. Once the part has been created, these loose particles can be removed, they can be reused after some treatment, and the construction that has been made using this printer can be post treated using heat or otherwise. Radiolaria Pavilion is an example that demonstrates how D-shape printer can be used for creating large structures in construction domain. In the picture is shown a 3D printed scaled model of real final pavilion. This example is of size 3 by 3 by 3 mm meter cube. The material used for this structure is calcium magnesium carbonate. Each layer is of 5 mm thickness and it took about 1 week to build this particular structure. This example shows how D-shape printer can be used for creating large monolith structures seamlessly and using a free form construction. This particular assembly was outcome of an experiment which was developed by Andrea Morgante of Shiro Studio in association with D-Shape Corporation, which is the company which made the D-Shape printers available in the market. Here is an example of on-site 3D printing of a part of a metal bridge. In construction domain, at times the parts can be so large that they cannot be built elsewhere and brought to the site of application. Thus, as you have seen in the other examples also, the construction needs to be done on site. In this case, the VAM process is being used. Additive manufacturing has been used for creating large buildings or large parts of buildings as well. The example on the left side shows how Epis Corporation has 3D printed a large house in Dubai. The material used in this case was a gypsum base mixture, and either the complete building can be printed as a monolith structure, or it can be printed into small parts, and those parts can be assembled. As you may all know, additive manufacturing has been extensively used for consumer goods also. Some of those examples are shown here. We will talk about specifics. It can be used for personalized glass frames. 3D scans of customers can be taken. Those scans can be used for creating CAD models in store, and then those CAD models can be used for printing those glass frames as per the requirements or as per the scan. This offers individualization and personalization. Similar is the case with teeth braces. Transparent or otherwise teeth braces can be printed. Shoe cushions can also be made using additive manufacturing. In this particular case, depending upon the load that is taken by the shoe cushion or the functionality of these cushions in various parts, different materials and the structure and process parameters can be used, so that the functionality is maintained. On the right side, there is an example of bicycle helmet, which has various complicated geometries, and depending upon the safety norms, various parts of this helmet uses various materials. For example, for better ventilation, this part can use complicated geometry so that there is good airflow. The other parts where better structural integrity is needed, some different material can be used, and also the type of geometry can be different as required. Additive manufacturing in consumer goods is driven by consumer needs. It offers rapid prototyping, quick repairs as needed. We do not need to buy the consumers do not need to buy the complete item. It can be repaired if repair is needed quickly. It is also driven by end user needs and personalization. For example, if specific designs are needed by customers, they can be created on demand. This also offers quick design and concept modeling iterations. Parts can be quickly designed and printed, and process can be modified to achieve what is required by the customer. It offers packaging innovations driven by rapid prototyping. For example, various types of containers and vessels as needed by the consumer can be created.
So, what is the scenario here? I mean, around the globe, not only in India, but around the globe, we have seen a lot of case studies today, right? So, how is it working? What's going on? So, what I would like to say is that there are different AM processes or technologies which are getting used across industry verticals. It could be very critical industries like aviation or medical that we saw, or it could be not so critical industry like let us say gaming for example, right, or hobby. Even those kind of industries are using additive manufacturing. Across materials, additive is getting used. So, it could be these bio generated materials, or it could be metal alloys. New alloys are getting added all the time, different kinds of polymers, ceramics, composites. So, across different kinds of material, additive is getting used. Across technologies, if you remember, we started off this particular course by discussing the different AM technologies and how they are classified according to ASTM, right. Now, again I want to iterate the point here that I have also said before, that no technology is better or inferior or anything like that. Each technology has its own strength and limitation. It is not that FFF technology, because it is very simple or easy, not that it is just used by hobbyists. No, even at in industry production floors, FFF technology is used. Laser powder bed fusion, not that it is used only for very critical components or anything like that. Hence, every technology is getting used in its own way across industries and materials. And value drivers. So, value drivers, again I want to stress that whenever somebody asks, can we 3D print this, we always ask why should we 3D print it, what is the value that additive manufacturing is adding, is there a pain point that you have which additive is going to solve. So, this value drivers is also very different. It could be customizing, it could be standardizing, it could be many number of parts, it could be few number of parts, it could be a few number of parts for a spare application, it could be many number of parts for a production scenario, right. So, the value that additive is adding is also different, but in multiples to any of these industries or applications. So, now that you have gone through almost the entire course, it is hopefully now it is more clear as to according to the application, the need and the regulations or certifications that are required, which technology will you choose and why you will choose. I hope that has become more and more clear, but I hope it has also become more clear as to what is the current industry scenario. So, that is the main aim of our course, not only to technically tell you, what is additive, what is possible and all, but also to let you know what are the possibilities, what is the current state of adoption of AM in the world and in India. And I hope that with these case studies we have been able to give you that message. So, here is a summary which is something that we are concluding the course with probably. So, for the conclusion I have a few slides on how India is adopting additive manufacturing. So, let us just go through that and then we will try to summarize for the week and the course. So, the strategy for additive manufacturing, it was launched on the 24th of February 2022. So, the year is missing there on the slide, but it is 2022. Now, they want to develop indigenous technological capabilities and they also want to tap and leverage the potential opportunities of the 4th industrial revolution, now of course moving to the 5th industrial revolution. The contents of the strategy would be outcome, industry wise opportunities, adoption barriers and focus areas. So, that is what we will go through also. Now, why I have taken this opportunity to kind of summarize the entire course using this is because it will help you gain insights as to in India what are the opportunities that we have, what support is the government of India offering and how can academia or an industry leverage this and participate in the AM workforce. So, let us first discuss about the strategy outcome. They have very clear strategies. I will just read them out. The first one is that they want 50 India specific technologies. So, when we say technologies, it is probably the processes itself, right, AM processes or maybe some customized post processing techniques like automatic support removal or something like that, these kind of processes. They are wanting to have 100 new startups and they will fund these startups in the initial days for a few years, give them mentorship, space to work and all of this. They would like to see 500 products that are developed using additive manufacturing. They wanted to penetrate into 10 manufacturing sectors. Here I would like to highlight one point. When I started with additive, it was about 11 years back. Everybody used to say that additive will replace so many processes, and it will be like revolutionary and all of that. So, what we have come to realize after at least my 11 years of career in AM is that additive will be another toolkit that is available for engineers. It is not going to replace casting completely or CNC machining, no, that will not happen. So, additive will be another process which will get integrated into the present manufacturing process. So, they would like additive to penetrate into about 10 manufacturing sectors. They would like to skill 1 lakh people with respect to additive, and this could be metallurgists, it could be designers, it could be operators of the machine, it could be application engineers, it could be in different domains. And they would like to raise the awareness and adoption of AM products. So, these are their specific strategy outcomes. Now, if I kind of summarize this into 3 points, then I would say basically what they are looking for is innovation and IP creation, be it in materials, machine, process, software or design. It is also to set up these manufacturing hubs and ecosystems with AM, and then develop the skill of the people so that these capital investments can be used very well. But what are the barriers to do this, right? One of the barrier is process and performance. So, this is listed in the strategy for additive manufacturing. So, they list that one of the barrier is process and performance. That is, there are, let us say 4-5 technologies to print with metal, and they are at a certain speed now, they print at a certain speed, which probably has to be much better or have more processes. When it comes to material, in casting you would have hundreds of metals that you can process, but maybe 30-50 in additive. So, that range of materials that can be printed has to improve. AM ecosystem, is there a powder manufacturer or a filament manufacturer in India? Is there a person who can do the finishing operation of AM parts very well? Is there a person who can machine the roots of a turbine blade, which are very complex? So, this along with AM, there are other things also which have to come up, including software. Are there business cases? So, where are the business cases? Is there MRO activity happening here such that one MRO company will approach and say, okay, let us make these 10 parts with AM because this is a good business case. So, do we have those business cases? Are we ready to qualify and certify the parts? Are there enough standards to do that? That is also another barrier. And then, do we have the legal framework, especially in design, right? Do we have processes in place which makes it easy for people to apply for IP, patent and all of these things? So, these are all listed as barriers. Now, 2 things here. One is that these barriers are across role, if you see, right. It could be a manager or a team lead or a CEO. It could be a legal person, it could be somebody who is related to quality, to material, to design, everything. So, AM is something that should be known to everybody in an organization or every department in an academic institution. It is not that only mechanical people should know it or only electronics, nothing like that. It is a very, it is a subject that everybody should be aware of. Now, even though these look as barriers, I feel that it is an opportunity. So, it is an opportunity for all of us to see which new material should we try and 3D print. which new part should we 3D print? Is there a variation in the process which will make the process more faster? So, that is the opportunity that we would have. So, even though they are mentioned as barriers, I would more like to look at them as opportunities. Now, let us look at the industries and what the strategy for additive manufacturing says about these different industries. So, aerospace, we do not have tier 1 aerospace industries in the country, what we have is tier 2 and tier 3, and probably that is what we will have to target for additive manufacturing, which may not be too many. But if you look at space, it is very different. So, aviation we do not have so many, but space we have a lot of startups now, and even ISRO uses additive a lot. So, space there is very high opportunity, maybe not so much in aviation. Defense, yes, a lot of materials which are getting custom made for defense and applications for them, that is a very big area. Medical, yes, considering India is a healthcare capital of the entire world. Electronics, Indians are very good at it, and if we can integrate these novel methods of manufacturing electronics, then that would be great as well. Automotive, huge volumes, but I think the technology has to still evolve a little bit to catch up with that. Maybe when it does, even automotive industry will be a power user of additive. Industrial, we have a lot of oil and gas, tooling industries, we have a lot of those. So, that is a really good market. Consumer care also, it could be gifting, it could be all these custom gifting ideas or things like that. So, India is a huge market there for toys and all of that. So, that is a good one also. Construction, our defense has actually constructed a few buildings, some are apartments, some are I think there is also a post office in Bangalore which has been 3D printed. So, there are quite few structures that they are trying to 3D print in the construction industry, and that would be really good for areas where it is difficult to take a lot of people and make a building. Instead, take a truck full of concrete and then use very few people to make structures. So, that is also coming up quite a bit because of the government. So, each industry is different, and there are different ways or different expectations from each industry. So, that is what we will have to understand when we try and cater to them. So, what should the focus area be? We have seen design, material, process and the entire value chain. Can we make design softwares? Can we make powder as well as develop the parameters to 3D print them? Can we make the process bigger, faster and more accurate? Can we make the machines itself? And then we have the value chain where we have the qualification, certification and all of these things. So, when you look at all of that, I think all of them will be possible only when you have the right applications, right. We have to mine for these applications which are a good fit for AM. For example, we have O2 Vent here, this is an Australian company, and it makes this device called as this device which will help people with sleep apnea. Basically, sleep apnea is a condition where the roof of the mouth collapses and then the person can't breathe, doesn't breathe, and sometimes can even pass away when they are asleep. So, this particular polymer 3D printed part when put in the mouth will help to keep the roof up and not collapse. So, it is a new company, Australian company. Optisys is a company which makes only additively printed RF antennas. So, the antenna that you are seeing that is fitting on his palm was actually like a feet long, but now it is very small, same function, even better function. So, Optisys has this entire business model where it only 3D prints the antennas that go into space. Whereas, so O2 Vent, Optisys are new companies, but if you look at Adroy over here, it is a very old company, it was founded in 1982. But having realized the value of additive manufacturing, now they have a sister company which 3D prints these kind of hydraulic manifolds. right, an old business, but then they found a new way of new advantage of additive manufacturing and they use it in their production. Then we have Siemens, which is using additive for repair. They have the blades which will be worn out, these blades they will grind and then they will again reuse it. So, they are using it for repair. So, what you see here is new company, new product, old product, but slightly different design, repair, much better design. So, across it is all about finding those right opportunities or finding those right applications for AM. So, hence I would like to conclude by asking, what will you create? What will you create? I hope this course inspires you to use additive in the best way possible in your domain, and the assignment that will be there for this week is also related to this. It is about putting up an idea of how you would use additive in your work. What would you use it for? And what is the pain point that it would solve, or what is the value add? Would you use metal or would you use polymer? How different would your design look? How much more better would your design or performance be? So, that is what we want to pick your brain on in the assignment, in the last assignment of this course, which is the week 4 assignment. So, keep watching the space to look at the assignment, and we are hoping to see brilliant and great ideas come out from all of you. So, thank you very much for taking the time to take this course. It has been a pleasure.